When an aircraft goes down, one of the first questions investigators ask is simple but critical. What happened to the engines? In the case of the Greg Biffle plane crash, that question has taken on significant weight because the engines at the heart of this investigation have a history that stretches back over 5 decades, powering thousands of business jets across the world. Today, we need to talk about what the NTSB is looking for when they examine those engines, what we know about the Pratt & Whitney Canada power plants that were on that citation, and why the engine manufacturer's involvement in this investigation matters more than you might think. Because the engines on that plane aren't just pieces of machinery, they're data recorders in their own right, and what investigators find inside them could be the key to understanding what went wrong in those final 10 minutes. The Cessna Citation 550 that crashed at Statesville Regional Airport on December 18th was powered by 2 Pratt & Whitney Canada JT15D-4 turbofan engines. Now, if you're not familiar with aviation engines, that designation might not mean much to you. But in the world of business jets, the JT15D series is legendary. These engines have been around since the early 1970s, and they've powered some of the most successful light jets ever built. The Citation II, the Beechjet 400, the Mitsubishi Diamond. All of them rely on variations of this engine. Over 6,000 JT15D engines have been produced, accumulating more than 41 million flight hours. That's a massive installed base, and it means that any systemic issue with these engines has the potential to affect hundreds of aircraft worldwide. Now here's what we know from the NTSB's initial briefings. Both engines were present with the main wreckage. That's significant because it tells us there wasn't a catastrophic in-flight separation where an engine detached from the aircraft. Both engines remained attached to the airframe throughout the sequence of events. Investigators documented the engines on site, and according to NTSB board member Michael Graham, Pratt & Whitney Canada is serving as a technical advisor to the investigation. That's standard procedure. When an accident involves a specific engine type, the manufacturer provides technical expertise to help investigators understand what they're looking at. They don't control the investigation. They don't write the reports. But they provide critical knowledge about how the engines are supposed to function and what failure modes are possible.
So what exactly are investigators looking for when they examine those engines? First, they're looking for signs of mechanical failure. Did one or both engines experience an internal failure that would have caused a loss of thrust? To answer that question, they need to conduct what's called a teardown inspection. The engines are carefully disassembled piece by piece, and every component is examined for signs of distress. They're looking for things like turbine blade fractures, compressor failures, bearing seizures, anything that would indicate the engine stopped producing power before impact. They're also looking for foreign object damage. If something was ingested into the engine, whether it's a bird, debris from the runway, or objects from an unsecured baggage compartment, it will leave telltale marks on the fan blades and internal components.
Now, one of the most discussed theories in the aviation community is that the Biffle plane may have had a baggage door open in flight, and that items from the forward baggage compartment were ingested into the right engine. There's some visual evidence to support this theory. Post-crash photos show what appears to be damage to the right engine's fan blades, and there are reports that the forward baggage door is missing from the wreckage. If that door opened shortly after takeoff, it's entirely possible that loose items could have been sucked into the engine inlet. The Citation's engines are mounted on the sides of the rear fuselage, and the forward baggage compartment is located in the nose. Depending on the airflow and the weight and size of the objects involved, it's plausible that debris could be drawn back toward the engines. There's precedent for this exact scenario. In 2024, a Citation II departing from Barranquilla Airport in Colombia experienced an opening of the right-hand nose baggage door shortly after liftoff. Items from the compartment were ingested into the number 2 engine, resulting in engine damage and failure. The crew successfully returned and landed on the remaining engine. That incident is eerily similar to what may have happened in the Biffle crash. The key difference is that the Barranquilla crew had enough altitude and airspeed to manage the situation and make a successful single-engine landing. The Biffle flight, by contrast, appears to have been in a much more constrained situation, operating at low altitude in marginal weather with very little margin for error. Here's where the engine investigation gets really important. If the teardown inspection reveals foreign object damage consistent with baggage ingestion, it would confirm one of the leading theories about what caused the emergency. But it would also raise a much bigger question. Why didn't the remaining engine provide enough thrust to keep the aircraft airborne? The Citation 550 is certified for single-engine operations. It's not a particularly powerful aircraft, and it doesn't have the climb performance of larger jets, but it's supposed to be able to maintain altitude and execute a safe landing with one engine operating. So if one engine failed due to foreign object ingestion, what prevented the crew from using the other engine to bring the plane home safely? There are several possibilities. One is that the crew may have been dealing with more than just an engine failure. If the baggage door was open and flailing in the airstream, it would have created massive drag. Drag is the enemy of climb performance. Even with one good engine producing full thrust, excessive drag can prevent an aircraft from climbing or even maintaining altitude. The citation manual specifically states that the aircraft cannot maintain altitude with landing gear down and full flaps, especially at maximum weight. If the crew had already extended the gear and flaps in preparation for landing, and if the open baggage door was creating additional drag, the aircraft may simply have been unable to generate enough lift to stay airborne. Another possibility is that both engines were affected. If debris ingestion damaged the right engine severely enough to cause a complete failure, it's possible that smaller debris or secondary effects impacted the left engine as well. Engines are finicky. Even minor foreign object damage can reduce thrust output significantly. If the left engine was producing reduced thrust, even if it hadn't failed completely, the aircraft's performance would have been degraded. Add in the drag from an open door, the weight of a fully loaded aircraft, and the configuration with gear and flaps extended, and you have a situation where the aircraft simply doesn't have enough energy to arrest its descent. Now let's talk about the JT-15D engine itself. This is a small turbofan engine, and by modern standards, it's relatively simple. It uses a centrifugal compressor for the high-pressure stage, which was a somewhat unusual design choice even when the engine was developed in the late 1960s. Most turbofan engines use axial compressors throughout, but the JT-15D's centrifugal design gave it certain advantages. It was compact, lightweight, and relatively easy to maintain. The early JT-15D-1 models produced around 2,200 pounds of thrust. The -4 variant used on the Citation 550 produces 2,500 pounds of thrust. That's a modest increase, but it made a significant difference in climb performance and cruise speed. The JT-15D-4 introduced an additional feature that earlier models didn't have: a booster stage located just behind the fan. This axial flow booster compresses the air before it enters the centrifugal compressor, which improves efficiency and thrust output at higher altitudes. It's one of the reasons the Citation 2 was able to cruise faster than the Citation 1. But it also means there are more moving parts, more potential failure points. The booster stage, the centrifugal compressor, the turbine sections. All of these components will be inspected during the teardown. Now, Pratt & Whitney Canada engines have an excellent overall safety record. The JT-15D series has logged tens of millions of flight hours with relatively few catastrophic failures, but that doesn't mean the engines are problem-free. Over the years, there have been airworthiness directives and service bulletins addressing specific issues. One of the most significant was an impeller failure issue that affected the JT-15D-1 series engines. Service history revealed 4 events of uncontained impeller failures, all of which resulted in penetration of the aircraft fuselage. Investigation determined that the root cause was surface irregularities on the rear face of the impeller, which led to crack initiation and propagation. In response, Transport Canada and the FAA issued airworthiness directives mandating borescope inspections of certain impellers. That issue primarily affected the -1 engines, not the -4 variant used on the Biffle plane. But it demonstrates that even well-proven engines can develop problems over time. Another issue that's been documented involves the JT-15D-5 engines, which are a later and more powerful variant used on aircraft like the Beechjet 400. There have been several reported incidents of high-altitude dual-engine flameout on JT-15D-5 powered aircraft operating in certain meteorological conditions. Investigation revealed that the fuel control hydromechanical unit could be exposed to excessive moisture and freezing, which could cause the servo to freeze and shut down fuel flow to the engines. The FAA issued an airworthiness directive requiring a modification to reroute compressor delivery air to improve moisture separation. Again, this issue affected the Dash 5 engines, not the Dash 4. But it's another example of how environmental conditions can interact with engine systems in unexpected ways. The point here isn't to suggest that the JT-15D engines are unsafe. They're not. Millions of flight hours prove that. But like any mechanical system, they have vulnerabilities, they have failure modes, and when an engine fails at a critical phase of flight, the consequences can be catastrophic. What investigators need to determine is whether the Biffle crash involved a known failure mode, a previously unidentified issue, or simply a cascading series of events that overwhelmed the crew's ability to respond. Here's what the engine examination will reveal.
First, whether one or both engines were producing thrust at the moment of impact. Investigators can determine this by examining the internal components. If an engine was running at high power when the aircraft hit the ground, the turbine blades and compressor stages will show specific patterns of damage. If the engine had already failed or was windmilling without producing thrust, the damage patterns will be different. Second, whether there was foreign object damage. If debris was ingested, it will leave marks. Gouges on the fan blades, dents in the inlet duct, damage to the compressor stages. Those marks tell a story about what the engine encountered and when. Third, whether there was a pre-existing mechanical problem. Fatigue cracks, bearing wear, oil starvation. Any of these could indicate that the engine was already compromised before the flight even began.
The maintenance history of the aircraft and its engines will also be critical. The Biffle plane was a 1981 Cessna Citation 550, which means it was over 4 decades old. Now, as former NTSB investigator Greg Feith pointed out, the age of an aircraft doesn't automatically mean it's unsafe. Aircraft are maintained to very high standards. If an aircraft is properly maintained, it can operate safely for many decades. But maintenance is everything. Engines have to be overhauled at regular intervals. Components have to be inspected and replaced. Any signs of wear or degradation have to be addressed immediately. The NTSB will review the complete maintenance logs for both engines. When were they last overhauled? What inspections were performed? Were there any squawks or discrepancies noted in recent flights? Were all airworthiness directives complied with?
These are the questions that will be answered as the investigation progresses. One thing that's important to understand is that engine failures, while serious, are not supposed to be catastrophic events. Multi-engine aircraft are designed to fly safely on one engine. Pilots are trained extensively on single-engine procedures. They practice engine-out takeoffs, engine-out landings, and engine failures at critical phases of flight. The Citation 550, like all multi-engine jets, has specific procedures for dealing with an engine failure. Identify the failed engine. Secure the failed engine. Maintain aircraft control. Configure for single-engine flight. Declare an emergency. Find a suitable place to land. These procedures are drilled into pilots until they become second nature. So why, in this case, did those procedures apparently not prevent the accident?
That's one of the central questions the NTSB will be trying to answer. Was it because the situation was more complex than a simple engine failure? Was there a combination of factors, engine failure plus configuration issues, plus weather, plus decision-making pressures, that created a scenario the crew couldn't manage? Was there something about the aircraft's performance that the crew didn't anticipate? These are difficult questions, and they require a careful, methodical investigation to answer. One of the things that makes this investigation particularly important is the potential for broader safety implications. If the teardown reveals a previously unknown failure mode with the JT-15D-4 engine, that information needs to be shared with the entire fleet of operators using that engine.
If the investigation reveals that baggage door security is a bigger issue than previously understood, that could lead to design changes or operational procedures to prevent similar events. If the investigation reveals that single-engine performance in the Citation 550 is more limited than pilots realize, especially in certain configurations, that could lead to changes in training or operating procedures. This is why the NTSB doesn't rush these investigations. They're not just trying to figure out what happened in this one accident. They're trying to identify systemic issues that could affect other flights, other aircraft, other crews. Now, let's talk about what we should expect in terms of timeline.
The NTSB will release a preliminary report within about 30 days of the accident. That report will include basic factual information about the engines, their serial numbers, their time since overhaul, any obvious damage observed during the initial examination. But it won't include the results of the teardown inspection. That takes time. The engines have to be transported to a facility equipped to perform the teardown. They have to be carefully disassembled under controlled conditions, with representatives from the NTSB, the FAA, Pratt & Whitney Canada, and possibly other parties observing. Every component has to be photographed, measured, and analyzed. Metallurgical testing may be required to determine how and why certain parts failed. The complete engine analysis could take several months. Once the teardown is complete, the findings will be incorporated into the final accident report, which typically takes 12 to 18 months to produce. That final report will include a detailed analysis of the engine's condition, their performance leading up to the accident, and any contributing factors related to engine operation or maintenance. It will also include safety recommendations if the investigation identifies issues that need to be addressed industry-wide. Here's what we know for certain right now. The engines on the Biffle plane were Pratt & Whitney Canada JT15D-4 turbofans. Both engines were present with the main wreckage. Investigators have documented the engines and have begun the process of examining them for signs of failure or damage. Pratt & Whitney Canada is assisting the investigation as a technical advisor. The preliminary report, expected within 30 days, will provide basic information about the engine's history and condition. And the final reports, expected in 12 to 18 months, will include a complete analysis of the engine's role in the accident sequence. What we don't know yet is whether one or both engines failed, what caused any failure that occurred, whether foreign object ingestion played a role, and how the engine's performance or lack thereof contributed to the final outcome. Those are the questions that the teardown inspection will answer. And those answers will be critical not just for understanding this accident, but for ensuring that similar accidents don't happen in the future. There's another aspect of this that's worth discussing, and that's the human factor. Even if the engine analysis reveals that one engine failed catastrophically, the question remains, could the crew have managed the situation differently? Could they have maintained altitude if they had kept the gear up and the flaps retracted? Could they have climbed to a safer altitude before attempting to return? Could they have accepted a longer approach or landed at a different airport with better weather? These are painful questions to ask, especially in the wake of a tragedy that claimed 7 lives. But they're necessary questions if we want to learn from this accident and prevent future ones. The reality is that aviation accidents almost never have a single cause. They're the result of multiple factors aligning in the worst possible way. A mechanical failure that might be manageable under normal circumstances becomes catastrophic when combined with bad weather, heavy weight, poor visibility, time pressure, and split-second decision-making. The NTSB's job is to untangle all of those factors and figure out which ones were most significant, which ones could have been prevented, and which ones point to broader systemic issues. One of the things that makes the engine investigation so important in this case is that it will help answer a fundamental question. Did the aircraft's performance limitations surprise the crew? If one engine failed, and the crew configured the aircraft for landing with gear and flaps extended, did they realize how quickly their energy state would deteriorate? Did they understand that the Citation 550, especially at heavy weight, might not be able to maintain altitude in that configuration? Or did they believe they had more performance margin than they actually had? These are questions that the cockpit voice recorder may help answer, but the engine data will provide critical context. There's also a question about training and experience. The Citation 550 can be flown single pilot with the appropriate exemption, but it's a demanding aircraft, especially in an emergency. Single engine performance is limited. The aircraft requires careful energy management. And when things go wrong, they can go wrong very quickly. If the pilot in command didn't have extensive recent experience in the Citation, or if there was confusion about roles and responsibilities in the cockpit, that could have contributed to the outcome. The engine investigation won't answer those questions directly, but it will help establish the performance envelope the crew was working within. At the end of the day, The engines are just one piece of a much larger puzzle.
The NTSB will examine the engines, the airframe, the flight controls, the avionics, the weather, the crew's training and experience, the aircraft's maintenance history, the airport facilities, and dozens of other factors. All of that information will be synthesized into a comprehensive understanding of what happened and why. The engine analysis is a critical component of that process, but it's not the whole story. What we can say right now is that the JT-15D engines on that citation are undergoing one of the most thorough examinations they'll ever receive. Every component will be inspected. Every failure mode will be considered. Every piece of data will be analyzed. And when the investigation is complete, we'll know whether the engines played a direct role in this tragedy or whether they were functioning as designed in a situation that had already spiraled beyond recovery. The involvement of Pratt & Whitney Canada in the investigation is both routine and significant. It's routine because engine manufacturers always participate as technical advisors when their products are involved in accidents. It's significant because it signals that the NTSB considers the engines to be a critical area of inquiry. If the NTSB thought the engines were obviously not a factor, they might not need as much technical support from the manufacturer. The fact that Pratt & Whitney is actively involved suggests that engine performance and condition are central questions in this investigation. For the aviation community, the engine investigation will provide valuable lessons regardless of what it finds. If it reveals a mechanical failure, operators of JT-15D-powered aircraft will want to know what to look for and how to prevent it. If it reveals that the engines were functioning normally, but the aircraft's performance was insufficient for the situation, pilots will want to understand the limitations and plan accordingly. If it reveals that foreign object ingestion from an unsecured door caused the failure, aircraft owners and operators will want to implement better procedures for checking baggage compartments before flight. Every finding, every data point, every lesson learned makes the next flight safer. This is why investigations like this matter. Not to assign blame, not to punish anyone, but to learn, to understand, to prevent the next accident. The engines on that citation have a story to tell, and over the coming months, as investigators carefully disassemble them and examine every component, that story will emerge. It may be a story of mechanical failure.
It may be a story of human decision-making under extreme pressure. It may be a story of multiple small problems combining into one catastrophic event. Whatever the story is, it's one we need to hear. Because 7 people lost their lives, and the only way to honor their memory is to make sure we learn everything we can from this tragedy. The preliminary report is coming soon. The engine teardown is underway, and the answers, slowly but surely, are taking shape. When they arrive, they'll change the way we think about engine reliability, single-engine performance, and emergency decision-making. And they'll remind us once again that aviation safety is built on the lessons of those who came before. This is how we learn. This is how we improve. And this is how we make sure the next generation of pilots has the knowledge and the tools they need to come home safely, every single time.